Good morning, ma'am. My name is J. Charanteja. I am from CSC AML third semester, second year. Today, my topic is about efficient situational scheduling of graph and workload on simple chip, multi-cores, and GPUs. The overview of my topic: graph workloads like social media networks, roadmaps, or recommendation systems are data intensive and irregular. They are not easy to run efficiently on modern hardware, especially multi-cores and GPUs. The paper Efficient Situational Schedules of Graph Workloads on Single Chip, Multi-Chips and GPUs tackle this problem by designing a scheduling strategy that adapts to both the structure of the graph and the hardware architecture. Irregularity, heterogenetic data movement. These are the three challenges in graph workloads. The core problem of these graph workloads are different graph algorithm behaviors differently, and graph inputs vary widely. So a one size fit all scheduling strategy does not work well. Traditional scheduling methods mid overload one core while undisturbing others. Don't fully utilize the GPUs. Ignore how graph structure efficient performance. The main goal is to create a situational scheduling strategy. Creates a situational scheduling strategy that adapts to graph structure and algorithm types. This might be a chain or something like that. Adapts to graph structure and algorithm types. Balance workload between CPU, multi-cores and GPU cores, maximizing power and efficiency. Hybrid task graph scheduling, a program-friendly model. This can help GPU and multi-cores to work efficiently. DAG and NLDS, distinct aware scheduling of CPU plus GPU heterogeneous systems. And now we are going to see the proper approach. They, pro- they possess a hybrid system that can dynamically detect whether the run whether to run a graph workload on the CPU or GPU or both, how to split the workload based on runtime profiling and graph characteristics. First one is situational scheduling. This is the core innovation. It uses statistic analysis and dynamic profiling and heuristic graphs or algorithms. Statistic analysis, understanding algorithm and graph structure before running. Dynamic profiling, measuring actual performance during execution. Hysteresis, picks the best compute and unit, CPU or GPU, or combined. Now the second one is partitioning strategy. The partition the graph based on node degree, connectivity, load balancing potential. This ensures GPU gets large regular workload. It's good at parallelism. CPU handles irregular or control heavy tasks. Dynamic task paralleling GPU scheduler for irregular graph computing. Final gradient parallelism, adaptive scheduling, superior super speeds. These three main points that come in dynamic task parallel GPU scheduling. Platform details, they implement this on single chip multi-core chip like an Intel graphics or CPU, integrated GPU such as Intel Gen GPU on the same die. This is important because communicational cost is lower than between separation CPU and GPU systems. They can share memory more easily. Undefined memories can be shared. They tested on multiple graphs, algorithms, BFS, PageRank, etc., and data sets, finding their scheduling improves performance by up to 3x over static scheduling. It outperforms both CPU and also GPU only versions. Better energy efficiency due to reducing ideal time and smarter resources uses. Graph partition based scheduling policy. As I said before, graph scheduling or graph partition means arranging the graph in a sorted order or in a ascending order. Real world GPU scheduling insights. NVIDIA's most room policy. NVIDIA is a GPU that is widely used in any computers for CPU and GPU performance. It extends the power of the computer or the machine that we use to run the graphs. Why this matters? As graph data becomes more common, efficient process is crucial. Integrated CPU plus GPU systems are becoming widely spread in mobile and laptops. This work shows how to intelligently use all computer resources. As I said, NVIDIA is a graphics card that can be used with CPU for more efficient performance. Emerging trends and future directions. AI driven scheduling, GPU runtime, scale out architectures, standardized benchmarks. These are the emerging tech uh, in this AI era, that every software is AI driven, and CPU runtime is also less, so that the product can be cost efficient by the use of AI, and the CPU GPU involvement is also fully efficient as well. Now coming to the conclusion, and I want to talk about some key points. Graph workloads are irregular and require adaptive scheduling. Graphs that are provided by any superior or any companies that are in unsorted manner, by using CPU GPU with AI, we can uh, sort the data into ascending order or descending order, or the order which they want, the client which they want, and also no signal hardware until is better for all graphic types. No signal hardware until is better for all graph types. Adaptiveness is the key for no signal hardware. Situational scheduling improves performance and energy efficiency. Partitions, the graph based on structural is critical. Using both CPU and GPU together is better than using one alone. Thank you, ma'am. Thank you for listening me patiently. Thank you.